Hello everyone, this is the third lecture in real analysis. In this lecture we are going to discuss the completeness axiom of real numbers. So we are going to prove that square root of 2 is not rational. We are going to define supremum and infimum. We are going to provide some examples of supremum and infimum. We are going to state the completeness axiom of R. And finally, we are going to show that square root of 2 is actually a real number. So let us recall that in the last two lectures, we have been trying to describe the set of real numbers, which we denote by R. And so far, we have mentioned that R satisfies the following axioms. R contains the set of rational numbers. R is a field, and we defined what a field is. That was in the first lecture, which, by the way, is linked down below in the description of this video. R is an ordered field. We defined an ordered field in the second lecture, which is also linked in the description of this video. And today we are going to discuss what it means that R is complete. So R satisfies all of these four axioms. And let us also recall that the set of rational numbers is the set of all quotients P over Q, where P is an integer and Q is a natural number. And actually Q is an ordered field with respect to the usual operations of addition and multiplication, the way we learned them in school. So the next theorem gives us an answer about why we need real numbers. So it turns out that square root of 2 is not a rational number because we may say, well, since Q is an ordered field, why don't we just use rational numbers and be done with it? Well, it turns out that square root of 2 is not a rational number, and there are a lot of other useful numbers that we may want to use that are not rational numbers. So this theorem basically gives us an explanation why some kind of extension of the set of rational numbers Q is needed for us to be able to work with numbers. So let us prove this theorem. So square root of 2 is not a rational number, and more precise statement of the theorem says that there does not exist an element x in Q. There does not exist a rational number such that x is positive and x squared is equal to 2. So we are going to prove this by contradiction. So by the way, you may remember that this symbol means contradiction, and it's just like two swords. So by contradiction. So let us assume that the theorem is not true. Let us assume that the statement of the theorem is not true. So it means that there does exist x rational number such that x is positive and x squared is equal to 2. So suppose that there exists x, a rational number, such that x is positive and x squared is equal to 2. So from this statement, we want to derive some kind of contradiction, some kind of nonsense. Let us try to understand what it means that x is a rational number. That x is a rational number means that x can be written as a quotient P over Q. So because x is a rational number, x is equal to P over Q for some P an integer and Q a natural number. So without loss of generality, we can assume that P and Q do not have any common factors. Without loss of generality, P and Q do not have common factors. And why is it so? So, for example, if we had that x was 4/6, we could cancel out the 2, and we could say that this is 2/3, and we could say that p is equal to 2 and q is equal to 3. So we would not say that p is equal to 4 and q is equal to 6. We would say that p is equal to 2 and q is equal to 3. That's just an example, but it gives you an idea that if p and q had common factors, we could just cancel them out, and we could always write x in such a way that x is equal to p over q, where p and q do not have common factors. All right, so we discussed that. So now let us try to understand what it means that x squared is equal to 2. So because x squared is equal to 2, we have that p over q squared is equal to 2. But this is true if and only if p squared is equal to 2q squared. So this is true if and only if p times p is equal to 2q squared. But this equality right here, it means that p must have a factor of 2. So, but then p has a factor of 2, so p can be written as 2 times p1, where p1 is an integer. All right, so then we can plug in p equals to 2p1 into this equality right here. So we have 2p1 squared is equal to 2q squared. So this is true if and only if 4p1 squared is equal to 2q squared, and we cancel out the 2, so we have 2p1 squared equals to q squared. So this is true if and only if q times q is equal to 2p1 squared. But then this means that q has a factor of 2. But then q is 2 times q1, where q1 is a natural number. So in summary, p has a factor of 2, so p is 2p1, where p1 is an integer, and q is 2q1, where q1 is a natural number. So both p and q have a factor of 2. However, we did say that p and q do not have common factors, but p and q do not have common factors. And this is a contradiction. So therefore, our assumption that square root of 2 is rational was wrong. So square root of 2 is not a rational number, and that finishes the proof of this theorem. So QED. So our next task is to formulate the completeness axiom of real numbers. We now understand that we need numbers that are beyond rational numbers. So it's gonna take us a few steps to formulate the completeness axiom of real numbers. And the first step is to define a set bounded from above, a set bounded from below, and we are going to define what is a supremum, and we are going to define what is an infimum. All right, so we are going to do this for any ordered field just because we can, but of course the set of real numbers is an ordered field, so this definition is true for the set of real numbers. Okay, so let F be an ordered field and let A be a subset of F. We say that A is bounded from above by an element alpha in F if for every x in A, x is less than or equal to alpha. And in this case, alpha is called an upper bound of A. So in this case, alpha is called an upper bound of A. And just to illustrate how it looks like in the case of real numbers, if this is a real line R, and if this is a set A, then alpha is going to be some number such that it's to the right of the set A. So if I take an element x in A, x is going to be to the left of alpha. Now let us discuss what it means that alpha is a supremum of A. Let us discuss what it means that alpha is a supremum of A. So if the set A is bounded from above, we say that alpha is a supremum of A if the first condition is that alpha is an upper bound of A that is for every x in A, x is less than or equal to alpha. And the second condition is that alpha is the smallest upper bound of A, the smallest upper bound of A. That is, for every C upper bound of A, C is greater than or equal to alpha. So if we take any other upper bound of A, it is greater than or equal to alpha. So again, how does it look for the set of real numbers? If I have an interval between 0 and 1, so if A is the interval from 0 to 1, not including 0, not including 1, then 1 is the supremum of A. And why is that? Because, first of all, 1 is an upper bound of the set A, right? So this number 1 is to the right of the set A. And if I take any other upper bound of the set A, C is going to be greater than or equal to 1. Now let us discuss what it means that a set is bounded from below. And I encourage you to think about what that means by analogy from the definition of the set bounded from above. So we say that the set A is bounded from below by an element beta in F if for every x in A, x is greater than or equal to beta. So in this case, beta is called a lower bound of A. So in this case, beta is called a lower bound of A. And so how does it look for the case of the set of real numbers? So if this is my set A, then any lower bound of the set A is going to be to the left of the set A. So beta is going to be to the left of the set A. So if I take any element x in A, it's going to be larger than or equal to beta. Now let us discuss what it means that beta is infimum of A. So if the set A is bounded from below, we say that beta is an infimum of A if, first of all, beta is a lower bound of A. Beta is a lower bound of A that is for every x in A, x is greater than or equal to beta. And the second condition is that beta is the largest lower bound of A. So beta is the largest lower bound of A. That is, for every B lower bound of A, B is less than or equal to beta. So any other lower bound of A is going to be smaller than or equal to R beta. And again, how does it look on example for a set of real numbers? So if I have a set, again, the interval from 0 to 1, just like we took it before. So if my set A is the interval from 0 to 1, then 0 is going to be the infimum of A. And why is that? And this is because 0 is a lower bound of the set A, because the point 0 is to the left of the set A. And if I take any other lower bound of the set A, is going to be less than or equal to 0. So this B here is less than or equal to 0. Okay, so we have completed this step of defining the sets bounded from below, the sets bounded from above, and infimum and supremum. This was the step toward formulating the completeness axiom of real numbers. So by the way, before we move to the next topic, I wanted to explain here that here we looked at the interval from 0 to 1, so we used our intuitive understanding of real numbers here. Of course, we have not defined what real numbers are yet. We have not explained the completeness axiom of real numbers. However, just for the sake of giving this example, we relied on our intuitive understanding of real numbers. So now that we defined a supremum and infimum, we can explain what it means that an ordered field is complete. So an ordered field F is complete if every set A, that is a subset of F, bounded from above, has a supremum alpha equals to supremum of A that is an element of F. So an ordered field is complete if every set bounded from above has a supremum that is an element of F. As we mentioned before, the set R is complete. So here is an axiom. The set R, which is an ordered field, is complete. So in other words, if I take any set A that is a subset of R, if it is bounded from above by some number B, then there exists alpha equals to supremum of A, which is an element of R. Now, it is very important to say that the supremum, alpha, doesn't have to belong to the set A. So note, alpha is not necessarily an element of A. And we are going to consider an example that will illustrate this. So we are going to state two statements that we will need in order to consider some examples. We are going to state these statements and then we will prove them in the next video. So the first statement is about the density of rationals in R. So it turns out that if we take any open interval, AB, that is a subset of R, it will always have a rational number in it. So there will always exist R in Q such that R is between A and B. So let us state this formally. So for every open interval AB that is a subset of R, where B is greater than A, there exists R in Q, so there exists a rational number R, such that R is between A and B. It just basically says that there are a lot of rational numbers in R. So if I take any interval, no matter how small, there will always be a rational number in it. And the second statement that we are going to need in order to consider some examples is the Archimedean principle. Archimedean principle. So Archimedean principle says the following. So suppose we have a positive number m. So let's just say that the length of this interval is m. And suppose we have another positive number epsilon. Let's just say that the length of this interval here is epsilon. So the Archimedean principle says that there exists a natural number n such that n epsilon is greater than m. So in other words, I can take this interval and repeat it n times in such a way that the n times epsilon is going to be greater than m. So let us write this down. So for every epsilon greater than 0, for every m real number, so it's actually true even if m is negative, there exists a natural number n such that n epsilon is greater than m. So sometimes we refer to Archimedean principle as follows. You can fill the ocean with drops. So if m is your ocean and if epsilon is your drop, so you can put enough drops into this ocean so that the number of drops times epsilon is larger than m. So let us now consider some examples. So in the first example, we have a set A that consists of all rational numbers that are strictly between 0 and 1. We want to prove that the supremum of the set A is 1. So let's just note that 1 does not belong to A, but we are going to show that supremum of A is equal to 1. So this is an example of the situation where the supremum of the set does not belong to the set. So it's a very important point to understand. So here I wrote the density of rationals. We just stated it before, but I wanted to restate it. So every open interval of R contains a rational number. Okay, so let us prove this. So let us try to recall the definition of the supremum. So we want to show two conditions. So the first condition is that 1 is an upper bound of A. 1 is an upper bound of A. And the second condition is that 1 is the smallest upper bound of A. Remember, that was the definition of supremum. So we are using that definition here. So let us prove the statement 1. So let us say that X is an element of A. Then X is less than 1 because every element of A is between 0 and 1, and we in particular are interested in the inequality X is less than 1. So every element of A is less than 1. So 1 is an upper bound of A. So we showed what we wanted to show in the statement 1. The second statement is that 1 should be the smallest upper bound of A. So how do we prove that? So suppose that C is a real number and it's some upper bound of A. So C is an upper bound of A. So we want to show that C is greater than or equal to 1, right? We want to show that 1 is the smallest upper bound of A. So if we take any other upper bound of A, it should be greater than or equal to 1. So we're going to show this by contradiction. So suppose that C is less than 1. So suppose that C is less than 1. So then we have this situation here. We have the number 1. We have the number C that is less than 1. So this interval from C to 1, it contains a rational number. So there exists a rational number R that is between C and 1. So then there exists a rational number such that R is greater than C and less than 1. We also have that C is greater than 0 because, for example, the number 1/2 is in A and C is an upper bound of the set A, so 1/2 is less than or equal to C. So C is actually greater than or equal to 1/2, so definitely it is greater than 0. So then coming back to this inequality, so we have 0 is less than C, less than R, less than 1. So therefore this number R is in between 0 and 1, but then it belongs to the set A. It's a rational number that is between 0 and 1. So hence R is in the set A, and at the same time R is larger than C. So there is a contradiction here. Do you see? R is greater than C and R is in A. That contradicts our assumption that C is an upper bound of the set A, right? So if C is upper bound of the set A, then we should have R is less than or equal to C. So this is a contradiction. So therefore our assumption that C is less than 1 was wrong. So therefore we showed that C is greater than or equal to 1, which completes the proof of the property 2. So QED. So we have shown that supremum of the set A is equal to 1. So our next example is actually going to show that square root of 2 is a real number. Remember, we showed that square root of 2 was not a rational number. But we never showed the square root of 2 is actually a real number. So we are going to do that now. So consider the set B that consists of all rational numbers such that their square is less than 2. We are going to show that there exists alpha, real number, such that alpha is a supremum of B, and we are going to show that this number alpha is actually square root of 2. And in order to do that, we are going to use the Archimedean principle, which we stated earlier. So for every epsilon greater than 0, for every real number m, there exists a natural number n such that n epsilon is greater than m. So let us consider the proof. So by the completeness axiom of real numbers, if the set B is bounded from above, then it has a supremum. So to prove the first statement, what we need to show is that the set B is bounded from above. So let us show that B is bounded from above. So let R be an element of B. We just need to show that R is less than some real number. So then R squared is greater than or equal to 0, less than 2, which is less than 4. So but R squared is less than 4 if and only if r is less than 2. So this inequality here implies that r is less than 2. But then 2 is an upper bound of the set B, so the set B is bounded from above. So hence B is bounded from above. So how does this prove statement 1? Well, by completeness axiom, since B is bounded from above, B has a supremum. So by the completeness axiom of real numbers, there exists alpha that is a supremum of the set B. So we showed statement 1. Okay, so this was statement 1. Now let us work on statement 2. So let us show that alpha squared is equal to 2. That's really what we want to show, right? So by trichotomy, either alpha squared is equal to 2, or alpha squared is less than 2, or alpha squared is larger than 2. So only one of these three possibilities holds. So we are going to, our strategy is going to be the following. We are going to assume that alpha squared is less than 2 and get a contradiction. And then we will assume that alpha squared is greater than 2 and we'll get a contradiction. And then we will conclude that alpha squared is equal to 2. Okay, so suppose that alpha squared is less than 2. So I'm going to state a fact. So fact 1, there exists a natural number n such that alpha plus 1 over n squared is less than 2. So this fact is not difficult to believe because if we have alpha squared is less than 2, and then we can make this 1 over n really small by choosing n large enough in such a way that alpha plus 1 over n squared is still less than 2. However, the complete proof of this statement, of this fact 1, uses the Archimedean principle. So this is true by Archimedean principle. And I'm going to leave it as an exercise for you to use Archimedean principle to show this inequality. Okay, so we have alpha plus 1 over n squared is less than 2. So let r be a rational number such that r is in between alpha and alpha plus 1 over n. So this is true by the density of rationals, right? Remember, every interval of real numbers contains a rational number. So if you look at the interval alpha to alpha plus n, it's going to contain a rational number. Okay, so then if we square r, is going to be less than alpha plus 1 over n squared, which is less than 2. So hence, r squared is less than 2, and r is a rational number. R is a rational number. So R belongs to the set B because the set B consists of exactly all of the rational numbers such that their square is less than 2. So what did we get here? We obtained that so R is an element of B and R is larger than alpha. Remember, R is larger than alpha. But alpha is a supremum of A, so alpha is an upper bound of the set B. So R, it should be less than or equal to alpha. So we have a contradiction here. Okay, so alpha squared less than 2 is not true. Now let us assume that alpha squared is greater than 2. Suppose that alpha squared is larger than 2. So then fact 2, there exists a natural number n such that alpha minus 1 over n squared is still larger than 2. So again, I'm not going to prove this in every detail, but it's not difficult to believe, because if you look at this inequality, alpha squared larger than 2, we can choose n large enough so that this number 1 over n is really, really small, so that if we subtract that from alpha and we square whatever we received, it's still greater than 2. So this is true by Archimedean principle. And again, I leave it as an exercise for you to prove. So let R be an element of B, then R squared is going to be less than 2. Remember, because this is how the set B is defined. But then 2 is less than alpha minus 1 over n squared. And this is greater than or equal to 0. So we have that alpha squared is less than alpha minus 1 over n squared. So, but then R is less than alpha minus 1 over n. So then alpha minus 1 over n is an upper bound of the set B. Then alpha minus 1 over n is an upper bound of the set B. However, alpha was the supremum of B. So it should be the smallest upper bound. So we should have that alpha is less than or equal to alpha minus 1 over n, because alpha is the smallest upper bound. But of course, this is not true. So this is how we get a contradiction. So we showed that alpha squared less than 2 is not true. We showed that alpha squared greater than 2 is not true. So therefore, alpha squared, hence alpha squared is equal to 2. And that's what we wanted to show. So Q, E, D. So going back to our example, we showed that square root of 2 is a real number. Square root of 2 is a real number. All right, so this is all for this video. Thank you for watching. Please put a like underneath this video, subscribe to this channel, and be good at math.